Good day, my name is Mark and I work in the Eclipse Trace Compass team. So today we will be doing a follow-up video following up on the recent video where we looked at the new LRUCache example contributed to the Trace Event Logger GitHub repository. So in that previous video we looked at how the simulation works at the code level. And in this one, we will concentrate on the instrumentation aspect and how everything is put together to obtain trace logs from it, from running it. So we will start by going through a little bit of necessary background information, mostly regarding the java.util.logging framework, JUL, as well as at the trace event logger level, how we extend JUL for tracing purposes. And then we will dig into the LRUCache example and look how we made it generate such pretty colorful and even useful traces that reveal the inner working of the simulation. So let's dig right in. Here I had ChatGPT just generate a summary of basic information about JUL. What to retain is that the JUL is the built-in logging framework for Java, so no need to have external libraries. It is there always. It has a few core components, a couple of which we will get into in slightly more detail. The logger is the part that you might be familiar with as a Java developer. So you would, in your application code, have things like logger.info and informative message. So the info here is the log level. If we look at the default log levels, so for when you use the logger in your application code, you might go to from finest to severe, and anything in between would be valid. And the all and the severe level are not useful, I think, for a logger, but they are useful for a handler. The handler is the component that is responsible to take a log record and format it, filter according, for example, to log level, and make sure that it reaches its destination. So different destination will have probably a different different handler, sorry. So if the destination is a console, you might use the console handler. If the destination is a file on your file system, you might use the file handler. So this is all nice and good, but in our case we want the trace log to be on the file system, so we might use the file handler, but is it good enough for that purpose? So to answer that, we can dig in a little bit into the file handler code. So we see that the file handler is extending the stream handler. That's the base class, which itself extends the handler base class that is abstract. One very key component of all the handler hierarchy is the public publish method. So this is the method that is called by the logger with a certain individual log record that needs to be pushed to its destination, filtered, formatted, and so on. So the filtering is happening in the isLoggable method. So according, for example, to log level, if you log at info level and the handler is configured to severe level, then that log will be discarded. It will not reach its destination. And but let's say that it is not filtered, it will end up being formatted, and then a flush will be called. So contrary to the flush that you might be familiar with at the using C++, this one will not guarantee that the entry will be in the file when it returns. However, at the Java level, it will guarantee that everything, all the buffers at the Java level have been flushed. So basically, when this returns, your log record is in the hands of the operating system. And more likely than not, it is just about to be published or saved, for example, in the file, in the case of the file handler. One thing to note, you notice that the publish method is synchronized, so this is important for us. In the context of tracing, there are two things that you want to always keep in mind. You want the tracing to not affect the performance of your application too much. So that's something big, but you also don't want your tracing to affect the timing of your application. So if you imagine having an application that has several threads, any of which can log, what could happen, especially if for a certain time slice, a bit of time, a lot of logging is happening, you might have more than one thread that will try to call to log, and eventually it will end up calling publish using your application thread each time, and only one will be allowed to execute the content of publish at a time. So you might have some threads that will need to wait and wait maybe multiple executions of publish by other threads before being let in. So that could cause a bit of a bottleneck on the performance, and that could as well throw off the synchronizations of your thread, or at least their natural synchronization, because some of them might wait more than their fair share for a bit of time, and that will cause potentially you to see things in the trace that would not be natural or would not happen normally, that instead would be caused by the tracing itself. So that's not very good. Which is why in the trace event logger we came up with a couple of our own handlers that extend JUL. So the most important one for the context of this video is the AsyncFileHandler. Like the file handler, it extends the stream handler, and it has its own built-in private file handler used to write to file. On top of this, to make it more performance and not affect the timing of your application thread, it will, instead of directly using a file handler, it will publish to a buffer that is a list of log records until that buffer is full, and when it is full, it will be flushed to a queue. And we will have a separate thread read from the queue and publish those log records. The other thing that can have the current buffer end up being flushed is a timer task that is configurable. It will execute periodically and flush the buffer to the queue. So that might be useful, for example, if the logging intensity of your application is not very intense generally or for a while, and you don't want your log records to just sit in the buffer without being on disk. Maybe you're tailing the log, for example, to see what is going on, or you're afraid that if your application crashes, you might lose these records. So yeah, it could be a good idea anyway once in a while to flush that buffer. To get all this working, we have a few configurable parameters. So the size of the buffer, the number of log record it can contain, how deep is the queue, and also for the periodic task to flush the buffer, how often should it be executed. So these default values are not necessarily super important. We will override them. We will see later how that's done. So here we have the asynchronous writer thread. That is really the key part of the async file handler. So we will see the incoming part just after, but this is on the output part. This thread will just run forever, or at least until it receives a close event, probably at the end of the execution of your application, and it pulls from the queue. This is blocking, so if there happens to be nothing in the queue, it will just wait there, and as soon as there is something, the thread will wake up and pull a list of log record, a buffer that was flushed in the queue previously by the incoming part of the handler. And once that is done, it will just iterate on that list and use its own internal private file handler to publish each record. So the publish here will go through the same code that we saw in the file handler. So for example, it will format and filter the log records according to the current log level and so on. On the incoming part, when you use the AsyncFileHandler and in your code an associated logger logs something, a trace, something related to tracing, instead of directly publishing, you see that the log record is just added to the current buffer. Then if the buffer is full, it will be flushed to the queue, added to the queue, and a new empty buffer will be created. You see that the first thing that happens though is the isLoggable check, and we have our own overridden version of isLoggable here. Its particularities are that there is a switch in the async handler to enable and disable logging, so you can dynamically in your program, if you like, dynamically enable, disable the logging, and if it happens to be disabled, then it will stop here. Then the private internal file handler is used to check for loggability. So we might discard some records here depending on log level. And finally, this handler is not meant necessarily for general use, or at least at the moment it is meant more for tracing related purposes. So if the current log record is of any type other than trace event log record, it will be discarded as not applicable, not loggable by this handler. So you have it. You can notice that the publish is still synchronized. However, your various application thread that would be logging, it should go really quick. It will check that the enablement of the handler and just queue in the end the log record to the buffer, and everything else will be taken care of by the writer thread that you're that is dedicated and does not use any of your times of your application's thread time. So that is the big gain versus just using the file handler. In Trace Event Logger, we have a second specialized handler, so I wanted to mention it quickly. This one is called a SnapshotHandler, and the idea is for this one that any log record will be added to an in-memory buffer that is configurable, and it will end up in there being classified by thread, and at the top level of the thread, the events there that have a beginning and an end. Every time an end event is registered, it will be checked against its beginning. The time it took will be computed, and if it goes beyond a configurable threshold in seconds, then the whole buffer will be flushed to disk or drained to disk. So you could see this is a bit like a flight recorder mode, where nothing will end up on disk. Things will just be in memory and really quick until something unexpected happens. So one of the top level trace segment for a given thread goes beyond a certain threshold. When that happens, the whole buffer or anything up to the size of the buffer, in-memory buffer, will be drained to disk. And the buffer is kind of like a circular one, so if ever it's not drained for a while and it reaches maximum capacity, then each time a new event or trace point is added to it, the oldest one will be discarded. This one, instead of writing in a file just of a given name, we can have the beginning of the file name is defined, and it will be automatically completed with the timestamp where when the event that caused the buffer to be drained to disk has happened. So there will be one file per drain, where you will have the full context up to the size of your buffer of traces in that specific log. And the beginning of the name is configurable. Okay, if we look quickly at the publish for the snapshot handler, all it does is to add the log record to the in-memory snapshot. We have the this function here. So quickly, a trace event that would end up being logged can have be of one of two interesting phases, beginning or end. If it's beginning, it is just added to the in-memory buffer. If it is end, then the corresponding beginning event is found, and the time is computed in seconds, and it is checked against the threshold. And if it goes above, then the in-memory buffer is drained to disk using a dedicated thread. So it will not just use your application thread that happens to have caused the drainage. So it should not. Your application should be safe from that point of view, and it will end up writing into the log on disk the whole in-memory buffer. So that's it for handlers. The last part of the background information I wanted to show you is in file LogUtils of the trace event logger. So I wanted to show a couple of things here quickly. The first one is we saw that the AsyncFileHandler only supports log record of type trace event log record. So this is where that is defined. And the only other thing I wanted to show here is this really useful utility function that permits to create a beginning and an end trace events with one call. It uses the Java autoclosable, so this relates to try blocks, meaning that we can create the beginning and end event for an arbitrary block of code that is wrapped using try. Something like this. This is not exact code, but you would create your new scope log in the between parentheses of the try in question, and it will end up creating a beginning event right there, right at the beginning of the block, and another one at the end of, and that event, when visualized, the beginning event will contain a label, so that label will be shown in Trace Compass visualizing the obtained log, and it will be marked with that label if long enough, or if you zoom in. And you can also log along with it an arbitrary number of arguments in the form of key value pairs, the key being a label and a value being an arbitrary string, for example, or value. So yeah, that is it. Now we are done with the background information. We can have a look at the LRUCache example and see which how we instrumented it to generate some nice trace logs that can be loaded in Trace Compass to get insights about the behavior underneath the surface. So we will need a logger. The scope log object, you give it a logger as one of its arguments. Just an anonymous logger is fine. And we will also obtain a reference to the AsyncFileHandler, so we will see how that is done. At first we pull the configuration for the simulation, and then we call initialize logging, where this is where the magic happens at the program level. So we use just an anonymous logger, and we call get handlers on it. and we expect to get an async file handler. We will see how that happens under the hood, and if that holds up to be true, we keep a reference on it. So that would permit to, for example, call the enable disable on it to enable and disable dynamically the trace logging as your application is running. So how is that possible that the JUL logger will get us a handler of AsyncFileHandler type? Well, through the magic of the properties file. So we have a properties file such as this one, and we defined as handlers a single one in this case, which is the fully qualified name for the AsyncFileHandler. And with that, we pass that property file. We will see how in a second when we start the application, and JUL will take over and configure loggers and handlers for us. So we can see that this is where we can configure where the trace log will end up. So in a subdirectory called traces and the name of the file trace.log, we have the how it will be formatted, and we can see that all the other configurations are related directly to the AsyncFileHandler. So as we saw, this will be the buffer size that we want. This will be the queue depth that we want, and the flush rate, or it would be maybe better name flush period. Yeah, 250 every 250 millisecond, the buffer will be flushed to the queue, such that trace events will not linger too long in the buffer. They will end up on disk sooner than later. And yeah, there are other parameters, but we will skip them for now. So now let's see how JUL will know about this particular properties file. So this is at startup. In our case, we run the simulation using the exec Maven plugin, but if you were to run it on the command line instead, it would be the same string here that you would use. You define java.util.logging config.file, and you point it towards your property file. And that is enough for JUL to load that file along with your application and instantiate for you the handler that you specified there with the parameters that you defined. So this is how the magic happens. Now, when we return from the initialize logging, everything is set up, and we can just log traces using ScopeLog objects, and they will end up being pushed to our async handler that is configured as we just saw. So just for convenience, here we create a scope log. This try block covers almost the whole execution of the main, so it should spawn the execution of the simulation. And we give it label, this label here. And as part of its argument, we just log along with the scope log the configuration of the current run of the simulation, all the important parameters, the cache size versus the data size, the number of reader threads, what delay to use to simulate a cache miss, delay between starting readers, and whether we want the warmup to be logged or not. And yeah, so that's the first trace point. It does not give necessarily insights about what is going on under the hood, but it can be practical when you generate a bunch of traces and you don't necessarily remember what each one corresponded to as far as the simulation parameters were that obtained that trace. So that can be useful for that purpose. And this is, once formatted, this is what the corresponding trace might look like in the trace log. So in this case, we have the first half of the scope log here, the beginning phase, the label, we use name here, and the parameters that were logged for that run. So that's right at the beginning of the obtained trace log, and right at the end, in a stack fashion, we will have the corresponding same PID TID end phase trace point. Together they will form a trace segment when we visualize it. And diffing the timestamp we will be able to know how long the whole execution has taken. So we will see the other trace points quickly that were added, the other scope logs in the main program. Sorry. So this is the only trace point or the only scope log pair of trace points that will give us insights about the inner working of the cache from the main program. The cache in question, it's a loading LRUCache. So the loading part means that when we create the cache, we provide it with the callback function, and the cache will use that callback when an element is requested from the cache and the cache does not have that element. So here the driver, the main, controls what the cache will do when an element is not present and is requested. So in other words, when this is called, this callback, anonymous callback function, we will know that a cache miss has occurred in the cache, and we will log a scope log for it. So we use this label, and we log a single argument with it that we call element, and it is the key that was used, in this case an index. So this is what this scope log will look like, for example, in the raw trace log, with its label as the name and beginning and end trace points. Okay, so now we go down into the main. We see we are in the warm-up section where the cache is exercised, so it gets populated. That phase uses a single thread, and the code executed in the thread is the sequential reader, which itself has a couple of scope logs in it. Yeah, so basically we expect that the scope log, since the thread block encompasses the whole of the warm-up, it will be when we visualize, it will be a segment on top of the warm-up sequential reader. After the warm-up phase, we have the proper execution of the simulation, where we create a certain configurable number of reader that will go from that will read basically all the data, cached data structure through the cache. So here we just create the various reader thread, and after that they will be waited for. And the sequential reader, so this is the code for the warm-up and the reader threads. We have a couple of trace points. So if you look at the try block corresponding to each one, this first trace point that will use the thread name as label will cover the whole of the execution of a given sequential reader, and then each reader will go from element 0 to max element and request them through the cache. So this second trace point here will encompass the execution of each iteration of the for loop. So it will give us context. If we imagine that we have already instrumented the cache, then instead of just seeing random accesses of the cache that we don't know exactly where they came from, this will anchor the context. We will see which reader thread or warm-up thread is doing the request, and we will see which iteration a given traces at the cache level map to. Okay, and this is an example of the raw trace generated by the trace points that we have seen so far that are in main. So unless you are a Neo from the matrix, the preferred way is probably not to read that raw log and try to understand it, though there might be cases where it is enough or it is useful to do so. But more generally, you will want to visualize such a log, and for that we have Trace Compass. Here we use the newer browser-based version through the CDT Cloud Blueprint application. There is the equivalent as well available for VS Code and VS Codium, and there is the classic Java-based Trace Compass that can be used as well. All right, so this run, the cache was slightly undersized, so 25 data element, the cache is size 24. What insights can we get just from the trace point added in the main? Well, we see during the warm-up phase, the warm-up thread is getting a cache miss every time. So the last level here, they are the trace points or the trace segments that map to the loader callback function being called by the cache, meaning there was a cache miss that happened. It is expected to have cache miss during the warm-up, but not necessarily right away with the cache that was just warmed up. So we can see all these here. They are reader thread cache miss. We have different readers, and reader 2 and 3 also register at least one cache miss. Another thing that might be a bit unexpected is that reader 1, 2, 3, 4, they are started with a little delay in between each one, but they end up all at the same time apparently, or really close together. So that is also a bit unexpected. If we zoom in on the first iteration of the warm-up, then we can see the label correctly on each of the trace segments. So we can confirm we have the warm-up thread, and then iteration 0, iteration 1, and so on. And for each one, we can see the load from slow storage ScopeLog, meaning that the callback loader function was called by the cache for each one of them, meaning a cache miss. Something to note here, so if any of you have ever played the old Tetris game, you might have the eye to notice that reader 1 has cache miss almost everywhere, and those basically there are 4 iterations when it's not getting a cache miss. However, we can see that other readers have cache miss at corresponding times, such that if we were just to lift the cache miss, we will have a cache miss for every iteration of the first reader. So just it's a little sign that we can use to note that there seems to be some type of unintended synchronization between the thread, the different readers. That should be normally, if everything goes normally, we would not expect such a synchronization. And we can zoom in a little bit on that, roughly that portion of the trace, looking at the loader ScopeLog, and we can notice that indeed we are in the area where reader 3 is starting, and it is iterating at first quite a bit faster than 1 and 2 that seem to be iterating at that point together at the same iteration value in their for loop, which is strange. Each iteration, one of the two seems to be calling the loader function and the other not. However, so that's a cache miss, and presumably that's a cache hit, but it takes the same time as a cache miss, so that is a bit strange. Reader 3, after having executed quite fast at the beginning, ends up just catching up to the first 2 readers, and it seems to be joining the iterating in sync with the first 2 at this point. Alright, so already probably we have a lot of insights just by instrumenting the main in this case, especially since we have a little bit of insight about internal cache misses through the loader function. But if we want to get the full details, we will need to add the scope logs also in the LRUCache code. So here we have the LRUCache code, and the key method in it is the get. The idea here is that there are a few code paths that we want to cover with our instrumentation. The first one being a cache hit, so we want the scope log for that, and if we zoom in we will see there is one. Then we have a synchronized block in the case of a cache miss when a certain value is requested from the cache. This synchronized block can have 2 code paths through it. So the thread that will register the cache miss for a certain element will execute that second part here. It is the proper cache miss followed by loading the value once it's obtained into the cache. And there is the first part here. If while the first thread is resolving the cache miss, another thread requests the same cache element, it will be blocked on the synchronized, it will not be permitted to execute the synchronized block content yet. It will wait until the first one has resolved the cache miss, and then it will be let in, and it will obtain a cache hit, but a cache hit that might have a wait time associated to it because it waited at the synchronized before being permitted to execute the synchronized block. And yeah, that part here at the bottom is the loading the value in the cache. So we have ScopeLog that cover all these cases. Then we can look the insert. We already covered it in the get. The insert will call evict LRU, this recently used, and this is where a check will be made. Do we have enough space in the cache to insert the current element that was just gotten from the loader function? And if not, we eject an element of the cache, the least recently used one that was tracked with the data structure. And finally, these are the last two trace points or scope logs that are added for the cache. So they complement the initial scope log that we add in the main. In this case here, they will save the performance counters and basically the results of the simulation run in the trace itself, while also printing them out on the standard out. So this way, the generated trace for a given simulation run will have which parameters were used with the first trace point in the main, and the result as well as the last elements in the log, or last scope log logged into that trace log. So for convenience. And if we load that into Trace Compass, we get the more stacks, we could call them, more deeper, for each thread, deeper trace. And at this zoom level, we cannot see for sure what each one is, but we already see the same one that we had earlier, the iterations of a given thread and the call of the loader function. One extra thing that we did not add before, there is more in there, but there is also this last line here, a little segment that seems to map in most cases to a cache miss or the loader function being called. However, during the warm-up, only the last element, the last iteration seems to have it. So we can guess what it is. It is most probably the eviction of an element. 25 data elements that are looped in, and the cache is size 24. So the last iteration, there needs to be an ejection, an eviction in the cache. If we zoom in on the first iteration of the warm-up thread, we can see the new trace segment, the synchronized block, the cache miss, load from storage we already had, and there is this new little segment here. If we zoom in and hover, we can see that it is the cache insertion. Now if we go to the last element or last iteration of the warm-up, where we had this new little segment at the bottom level, and if we want to confirm what it is, we can zoom in and we can see indeed it is an element of the cache that was evicted to make space for the insertion. For that scope log, we have logged one argument, which was the key corresponding to that element that was evicted. So if we want to get to that, we can just open the events table, select a time just in front of that event, and it should find it, and we can see in the args section that it was a cache element 0 that was evicted at the last iteration. So without going into too much detail, basically because of the least recently used algorithm, and because of the fact that the reader that uses the cache in this case always read from first to last element, this is an unfortunate situation because the cache is not quite big enough to cache the whole data structure, and the hole in the cache is will propagate forward. So now we are removing evicting element with key 0, and the first reader thread, it will be the first element it will ask. It will result in a cache miss, and then it will need to evict another element, and at that point the least recently used one will be key 1, which is the one that will be needed at the next iteration. So we're always evicting the element that would have been useful at the following iteration. So this is what is happening here. So if we zoom in on the reader threads, after a few iterations, so at around iteration 7, we can now, with the benefit of having instrumentation in the cache as well, try to understand a little bit more what is going on. So at this point, the two threads seem to be in sync, iterating on the same element at the same time. They both request element key index 7. One of them, in this case it's reader 2, gets there first, enters the synchronized block, which blocks it for the other thread, and then resolves the cache miss, calling the loader function from main. So at this point, it's just a delay in the simulation. In real life, maybe a database query or a slow read from a network disk would be done to resolve, get that element and send it back to the cache so it can be inserted, and another element will need to be evicted because the cache is full at this point, and we have always one extra element that we're trying to add, so we need to evict something else. The second thread that arrived at the synchronized block just needs to wait until this is all resolved, and then it can get the value from the cache, but after having waited. So this little segment here, cache it after wait, that confirms it. So if we zoom in, so this is the place iteration 12. So at this point, reader 1, 2, and 3 are iterating on the same element, and the reader 4 is just getting started. So it's a matter of timing, but in short, the further reader that is started with a delay will benefit, at least at the beginning, from a cache that has been filled in by the previous reader threads, and so it will iterate quickly while the other ones are waiting for one of them to resolve the cache miss and get the value. So we can confirm by zooming in on this element here, and yes, indeed, this scope log, this trace segment, is a cache hit. So the reader 4 at that point in time is just getting genuine, quick cache hits. Okay, so that is roughly it when it comes to the trace points. I did here a little experiment that I wanted to show you. So it seems that there's no bug as such in the LRUCache, or neither in the driver main program, but it is rather the fact that the main program reads always sequentially in the same order, and at the same time the cache is just configured slightly undersized. Those two things together end up being a perfect storm of bad performance for this specific simulation. So what if instead of using the evict least recently used algorithm, instead I used a really simple and surely not very optimized algorithm of evicting a random entry in the cache, just to compare. So this is the code that would do that. So pick an element at random to evict, and in the insert function I comment out using evict LRU, and I use the evict random instead. So we can see if this improved things or not by rerunning the simulation with this code and capturing a trace and opening it in Trace Compass. And yes, indeed, if you see the time each segment takes for each of the reader, it is much, much faster. The warm-up, compared to the warm-up, it is maybe a fifth of the time for each reader or something close to that. And we can see clearly that whenever a cache miss happens in any one of the readers, so we have between 1 and 3 cache miss for a given reader. So that confirms that in this scenario, that is based on a real-life example that we investigated, one of two things needs to be true if you want performance of this setup. So either you need to make sure that the cache is big enough to contain all the data elements, or you need to use an algorithm other than LRU if you want performance. So this is just zooming in on one of the readers using the random eviction. So yeah, there was one cache miss in this example here. And this is the various readers zoomed in so we can see them together. Okay, so one thing that I have not covered yet, you might be wondering about the coloring of the different segments when we load the trace in Trace Compass. So to show it in all its glory, we need to have run the simulation with more iterations. So we need to have more cacheable elements and a bigger cache. And also proportionally, I increase the number of the time between starting each reader. The rest stays the same, still 4 threads. So this is the result, and you can see that it is even more colorful than what we had seen so far. And I will explain briefly how the colors are generated automatically by Trace Compass. So the colors for each segment or each scope log will be automatically generated, a bit of a kind of a hashing algorithm by Trace Compass based on the name or label of each segment. The first character has the most weight in the final color, and as we go deeper into a longer string, they have less and less impact. So for a scope log that is just a static value like warmup, it will always be the same color based on the getting a color value from the various characters. Same for the configuration here, it's always the same static string, it will always be the same color. You notice that the iterations, the second level for each thread, whether it's a warmup or a runtime reader, the color is not static, it changes as we go through the iterations. It's because the label associated with each iteration contains the iteration number, and so it will, from one iteration to the next, change a little bit. So, for example, it will go from 0001 to 0002. The first part, up until 0 here, will determine the base color, and then there will be a little changing part at the end that will not necessarily be visible from a few iterations apart. However, at each 10 iterations, we will go, for example, from 09 to 10. So this is, in this case, the one more significative level character is changed that is closer to the beginning of the string. So there will be a bigger change in the resulting color here, and in theory, even bigger one at each 100. So already from that, if we zoom in a bit, you can kind of see, it's not super clear for each transition, but you can see little segments. Each represent 10 iterations from 0 to 9. Another thing that we can see is that we go through one full spectrum from the beginning of the iteration to about roughly here. And we don't complete quite a second one, it stops at green, so we're missing like a little bit to have 2 complete cycles of color in this example where we have 250 iterations. So is that useful? Well, kind of. Let's see. So reader 1 takes the same time to execute as the warm-up, and then we have reader 2 that takes a bit less, reader 3 a bit less even, and reader 4 that is the quickest. Just based on the color of the iteration scope logs, we can see, we can have an idea what is going on. If you look here, the transitions of color, we have the same one in the beginning of the second reader, just compressed. So from that, we can understand that it goes through the same iterations, just much quicker. It's even more so, more iterations are compressed here for reader 3, where we have the same spectrum as we have here. And after that, they're all the same, right? And reader 4, even more compressed at the beginning. So in this case, we could see roughly half of its execution is compressed into this little segment. And after that, it's the same as the other 3 readers. So in every one of those cases, the compressed segment is just the given reader going quickly through the first iterations because it has been benefiting from a cache that has been where all the holes have been plugged by the previous readers. So running the same simulation with the 250 iteration, but using the alternative random eviction algorithm, we can see that the increased performance holds with more iterations as well. Zooming in on one of the readers of that run, there is maybe around 20 cache miss out of 250, which is not great. It is random after all. We don't expect that it will have an ideal outcome, but it is way better than LRU for that setup. And a final example I wanted to show you. So I had the idea to, after the warm-up, have a little loop that will perform 1,000 random reads into the cache. Just one element selected at random for each iteration, such that it would scramble the cache and the holes will not be contiguous at the beginning of the cache when we start executing the readers. And we can see that it helped momentarily. Reader 1 has had a pretty good runtime similar to the random eviction algorithm. However, it's only a matter of time that the readers will put back the holes in the cache in order, and we can see that by the time it is with reader 2 and 3, they end up being in sync together with the Tetris pattern appearing, and also using the color of the iterations. We can see that they are similar at the beginning with a similar execution time, but after a little while we have reader 2 is iterating, is taking more time for this part of the iteration versus 3. And yeah, reader 4 ends up being lucky at the beginning and joining towards the end the synchronized pattern with reader 2 and 3. So I expect that if we were to run, wait a little bit and run more readers, then it will look exactly like it looked in the previous example with LRUCache. It would be bad. So this is not a fix. Randomizing, using random accesses as part of the warm-up will have a momentary positive effect, but it will not fix the core issue that LRU and sequential reading and a slightly undersized cache is not a good idea. So that is it. Thank you for the attention. I hope it was informative, and see you next time.